Welcome. I'm proud to present the first available model of interactions between electromagnetic fields in space environment and air currents in atmosphere. Everything what you're going to hear in this movie is based on a relatively young branch of science called magnetohydrodynamics. Although the term sounds rather scary, to understand this subject you just need the knowledge at high school level. However, in order to explain this subject properly, I need to add couple additional terms and change slightly some things about which we learn in schools. I'll begin with the basics. That means magnetic fields and their role in the environment in which we exist. According to official and scientific knowledge, existence of magnetic fields is just a side effect of electric currents. Motion of energetic particles creates by induction its own magnetic field perpendicular to the direction of current. However, things which we've discovered in last couple decades of space exploration can be explained using this process. For example, let's look at plasma ropes which are hovering above the surface of Sun or magnetic connections between galaxies. To understand those phenomena, we need to turn upside down the correlation between plasma and magnetic fields. According to the current knowledge, magnetic field of Sun is frozen within the solar wind plasma. But in reality, energetic particles are being guided by magnetic field lines, which don't have any physical properties, and we don't know any material carriers which could be their building bricks. As another example, I can use the atmospheric discharge. That means, of course, lightning. It seems that ionization of neutral particles starts before the discharge. It can be explained using magnetic connections between opposite potentials. Particles which create the lightning follow such connections. This could mean that magnetic field lines are faster than matter and possibly can reach the speed of light. Another subject is the penetrability of magnetic fields. We all know that matter, which is a good conductor, aligns itself along magnetic field lines. But more important is the fact that magnetic field can easily penetrate matter which doesn't have conducting properties. That's why metal objects placed on a wooden table will follow the movement of a magnet placed under the furniture. This property of magnetic fields is crucial for my model. According to the current knowledge, interactions between Earth and space environments end on the ionosphere, where plasma currents are being cut out by the layer of ionized particles of air. No one, however, won't tell you that if geomagnetic field is being generated in the Earth's core and extends itself hundreds of thousands kilometers in space, its magnetic field lines have to pass through the neutral atmosphere, which is filled with natural conductors, like water vapor. So even if the direct influence of solar wind is limited greatly by the ionosphere, it's logical that geomagnetic field lines have to physically affect the water vapor in atmosphere. Okay, now I can start to explain the basics of magnetohydrodynamics and my model of electromagnetic influence on atmosphere. The most important process is known as magnetic reconnection. It means a rapid reconfiguration of field lines connections within electromagnetic fields, which is often followed by emission of energy into the environment. This process is the main cause of the most dangerous and spectacular events in space, like solar flares or auroras. It is as well crucial in understanding the dynamics of magnetosphere. Another process which I need to explain is known as flux tube. It is a kind of electromagnetic tunnel created by helical motion of particles along two magnetic field lines with opposite orientations. Process of flux tube creation starts when two electromagnetic fields with opposite electric potentials will move close enough to each other to allow them to connect magnetically. One field line is directed from field A to field B, and second one from field B to field A. It is the basic rule of electricity. Circuit has to be close to allow the flow of current. Using such connection, both fields can exchange their electric charges until the differential won't be nullified. Plasma ropes on the Sun, about which I've spoke before, are probably the best examples of such flux tubes, but each kind of electric discharge works according to the same rules. Okay, let's go further. Time to speak about the methods in which we describe magnetic fields in space. Probably the best way to explain magnetic fields is to use GSE coordinates, which describe the field lines in three values, which correspond with three physical dimensions: BZ, north-south orientation, BY, west-east orientation, and BX, Earth-Sun orientation. Positive or negative values of those components in nanoteslas show what is the direction and magnitude of a field. On the SWMF simulation there are three types of field lines: blue ones, which show the interplanetary magnetic field, or IMF, red ones, which show closed field lines with both ends connected to the planet, and black lines, which are connected to Earth only from one side, while second end is connected to IMF. Open field lines create and shape the lobes in magnetotail. Colors represent the density of plasma, with red high and blue low density. In the same way we can describe the magnetic field of Sun. Open field lines create and shape the heliosphere, which in fact is the local IMF for Earth. Closed field lines are responsible for the plasma ropes, which I was showing you earlier. Just like in magnetosphere, so in heliosphere, magnetic reconnection can take place between open and closed field lines. Reconnection is possible as well between the magnetic fields of Earth and Sun. Such short-time connections of open field lines are called flux transfer events, or FTE. On the Sun, areas where open field lines stick out from the surface are visible as so-called coronal holes. Let's move back to magnetosphere. Closed field lines are responsible here for the shape and condition of inner layer, which is called plasmasphere. Plasmasphere contains big amount of trapped energetic particles, electrons and protons, which create Van Allen belts and ring current. Those energetic particles moving in a current create by induction their own magnetic field, which works like a Faraday's cage and prevent the IMF from connecting to the planet at lower geographic latitudes. Sadly, during my observations I saw very often that plasmasphere was completely depleted in the matter of couple hours. I guess that the lack of charge in ring current can cause serious disturbances of weather patterns on Earth, but I'll go back to it later. All magnetic fields have poles and polarities. Polarity of Sun is responsible for the magnetic orientation of IMF. Open field lines, which are separated by neutral sheet current, create sectors of heliosphere, in which IMF field lines are pointing outward or towards the Sun. I think that the outflow of plasma from plasmasphere is caused by rapid changes of IMF orientations, which takes place when Earth moved from one sector to another. When the environment of Earth changes rapidly its magnetic orientation, particles which were trapped in inner magnetosphere before don't align with the new configuration of open field lines, and they have to be replaced by new particles caged in the sector to which Earth just moved in. But let's see how it works in real life. I'll begin with the most known process. That means geomagnetic storms caused by enhanced solar activity and negative values of BZ component, IMF field lines directed southward. Such direction of IMF allow a connection with open field lines of magnetosphere, what results in the inflow of solar wind particles to the ionosphere in the areas where magnetic field is weaker. In magnetosphere, such points are called polar cusps, and they are placed over magnetic poles. This process creates auroras. On this short movie, we can see how looks magnetic reconnection caused by negative BZ values of IMF. This process is known as substorm, and is one of the main causes of geomagnetic storms. However, not entire energy gets to Earth. Part of particles which are moving along a reconnected field line is ejected to space as a bubble of plasma. Such bubbles are called by scientists as plasmoids. Later I will try to explain how important is this process to our climate. Now let's compare this knowledge with the SWMF plus RCM magnetosphere simulation, which I've ordered in CCMC some time ago and which shows the behavior of magnetosphere in the first 3 days of December 2015. First, let's look at a reconnection caused by southward IMF orientation, or so-called substorm. As an example, I'll use an event which took place around noon in the first day of December. This graph shows the value of BZ component in IMF recorded by ACE satellite. Black arrows point out the fragment which I'm interested in. Visible drop of magnitude. In this period of time, BZ reached maximally -6 nanoteslas, what is enough to trigger small disturbances of geomagnetic field. This graph shows the readings from ground magnetometers placed in stations participating in TIMI's mission. We can see clearly the disturbances caused by substorm. I pointed them out with red arrows. Time to check the simulation. On the right side of images, we will see how the blue IMF field lines turn southward when BZ will become negative. Such orientation of field lines means that Earth moved to a sector with negative BZ component. Couple minutes later, a reconnection takes place in the magnetotail. Look carefully, as this process is hard to notice. In this area, open magnetospheric field lines are being squeezed by the IMF. When they touch each other, a reconnection takes place and open field lines turns into a closed one. Part of energy is being injected back to the inner magnetosphere. On this view, this process can be visible little bit better. Although it might look pretty innocent, those events are capable to shake the magnetic field over bigger part of the planet. This monitor shows the electric potential of ionosphere. Look how the shift of IMF affected the placement and charge of electric potentials over the magnetic poles of Earth. After the direction of current flow was rearranged to the new magnetic orientation of IMF, exchange of energy between Earth and solar wind can take place. Potential of ionosphere starts to grow visibly. Finally, it reaches the values slightly above 60 and -60 kV, twice so much as the neutral value, around 30 -30 kV. But as I said before, geomagnetic activity caused by the substorm was rather weak. During bigger geomagnetic storms, potential can grow couple times bigger. Here we can see data recorded by one of 5 TIMI's satellites. Graph on top of this chart shows auroral electrojet, or AE index. It represents the amount of energy which was transferred into the ionosphere with the particles of solar wind plasma, which is responsible for the auroras. On lower graphs, we can see disturbances of energy and directions of plasma currents in magnetosphere. As I said before, geomagnetic disturbances caused by the substorm on 1st December were rather weak, but as all substorms, this event managed to transfer enough plasma to cause weak aurora, which was captured by one of cameras mounted on ground station in North America. Although aurora was barely visible, this graph confirms it. On this graph we can see all substorms which were detected on the surface during first day of December. They are marked with red vertical lines. As you can see, during the time when negative BZ was dominating in the IMF, there were 3 substorm events and last one transferred more energy than 2 earlier ones. Now it's time to see what was the behavior of magnetosphere during the entire period of time on the SWMF plus RCM simulation. Such squeezing of open field lines into the magnetotail means an inflow of plasma into the Earth's environment. Closed field lines being ripped apart into open ones means that there is outflow of particles from plasma sphere. And this is generally everything what space science can tell you about reconnections in magnetotail. Almost everything what you will hear from now on is nothing more than my own conclusions which I've made during my research. You need to know as well that astrophysics and magnetohydrodynamics are only my hobbies, and my education has nothing to do with those subjects. It would be hard to call me an authority in the world of science. However, I can assure you that I made everything what I could to make this movie as reliable as it can be. Now let's check couple graphs which show geomagnetic effects of space weather activity. First one shows the AE index measured on the surface. It is clear that inflow of energy was possible only after the orientation of IMF turned to the south. Here we have couple readings from different ground magnetometers on which we can see clearly geomagnetic disturbances caused by substorms. Same disturbances can be seen on many different charts all around the globe. It is so because substorms caused by southward IMF orientation affect the geomagnetic field on global scale and are being recorded over a big part of the planet. However, on the data recorded in stations which are placed at lower geographic latitudes, there are almost no signs of activity during this day. It is because the magnitude of geomagnetic field which is much higher closer to the equator, and the particles trapped in the plasma sphere which generate their own magnetic field which cuts out the connections with IMF. All of this can't explain, however, other readings which are recorded in different parts of the globe. On those graphs, geomagnetic disturbances don't match with the timing of substorms. Just look at the data recorded in stations placed on the Greenland. It seems that negative BZ in IMF didn't affect their local geomagnetic field almost at all. However, two strong disturbances took place before and after the substorms. The same two impulses are visible as well on graphs from stations placed in North America. However, they are much weaker than the disturbances which were caused by southward IMF orientation. Let's make it even more funny by adding the fact that during the time of first geomagnetic impulse, past 1st AM, all sky camera in Greenland recorded quite bright aurora, which is visible here much better than the one triggered by substorm. If we look at the value of BZ component on the data recorded by ACE satellite, we won't find almost anything what could explain those impulses in Greenland. Although in the morning there is a small shift of BZ orientation, but it's rather too small and too rapid to be blamed for those geomagnetic disturbances. There is nothing what could explain the evening pulse, which was stronger than the one in the morning. Everything starts to be obvious when we look at the graph which includes all three components of IMF. Now we can see clearly the shifts of orientation which were most likely responsible for the disturbances recorded in Greenland. Official science can explain only one kind of reconnection, the one caused by negative value of BZ component in IMF. However, data which I presented shows clearly that magnetic reconnection can take place in all three dimensions. On the data recorded by TIMIS satellites, we can clearly see disturbances which took place soon before the IMF turned south. In the difference to substorms, which are visible couple hours later, there was almost no inflow of energy to the ionosphere. AE index didn't change almost at all. This data was recorded by another TIMIS spacecraft. In the difference to previous one, this satellite orbits the moon, and during the time when it is placed beyond the magnetosphere, readings are not distorted by the magnetic field of Earth. During the time soon before substorms, we can see that on the magnetometer readings there is a visible shift of BY component. BZ and BX didn't change almost at all, and oscillated around zero. So this time IMF field lines turned from west to east. Now let's look at the SWMF plus RCM simulation during this period of time. And now it gets more interesting. What we can see on this image is known as plasmoid, plasma bubble which leaves the magnetosphere and is transferred to IMF. And here we can see the magnetic reconnection which took place before the plasma outflow. To ensure ourselves, let's look at data recorded by one of GOES satellites, which are placed on the geostationary orbit, much closer to Earth than Themis crafts. On this graph we can see clearly both events, reconnection caused by shift of BY component and by the substorm soon after. Notice that on the lower graphs, which represent the densities and energies of protons and electrons, we can see a clear increase of particles during the time when BZ became negative. It is connected with the growth of AE index. Another interesting thing is the bottom graph, which shows the X-ray measurements. Those readings are connected mostly with solar flares. As you can see, there was a visible activity recorded soon after the BY reconnection. But let's go back to the geomagnetic pulse recorded in the morning by station placed in Greenland. Let's see what in the same time was recorded by Themis satellites. There is no doubt that there was a visible disturbance in the inner magnetosphere. This time it was connected with a small growth of AE index. On the satellite which orbits the Moon, we can see the most possible cause of this activity, a clear shift of IMF orientation. This time BX and BY components were the most affected ones. BZ changed only a bit. Again, the entire event was recorded as well by GOES satellites. We can see here a small inflow of particles into the geostationary environment. And again, a small increase of X-rays was recorded soon after the geomagnetic disturbance. It can be a response from the Sun for the reconnection between IMF and magnetosphere. This would mean that the planets communicate all the time with the star and the exchange of information is faster than the light. But this is not the time to speak about it. Because now I would like to show you what was the reaction of magnetosphere for the morning shift of IMF orientation on the SWMF plus RCM simulation. On the Z-CAD view it can be seen better as it shows the magnetosphere from above. In the moment when BX component started to dominate in the local IMF, blue field lines became almost totally horizontal. In the magnetotail we can see the pressure of magnetic field which was directed from the Earth towards the Sun. Such kind of magnetic reconnection is typical for the domination of BY component in the IMF. In such case, magnetosphere connects to the IMF in east-west orientation by creating a giant vortex in the magnetotail. During this event, BY reconnection allowed the inflow of plasma into ionosphere, what caused a small outburst of aurora. Because the connection took place in a different orientation, geomagnetic field was disturbed locally. This is probably the best explanation for the weird aurora which was recorded over Greenland right in the same time. However, auroras caused by BY domination are not a common sight, as reconnections which take place on the equatorial plane are mostly responsible for the outflows of plasma from the ionosphere and atmosphere. And this is the main subject of my research. Couple minutes ago I was showing you how the energy inflow during the substorm raised and stabilized electric potentials of the ionosphere. Now I will show you what happens during opposite process. That means outflow of plasma from the Earth's environment. This is the reaction of ionosphere for the morning shift of IMF orientation. And this is the behavior of ionospheric electric potential during the reconnection soon before the substorms. Differences are rather obvious. During the plasma discharges, electric potential of ionosphere drops drastically and the locations of charges become very unstable. During BX and BY reconnections, electric potential move often to lower geographic latitudes, as open magnetospheric field lines are being pulled by the IMF to the equatorial plane.